Relation. Relation is the set of ordered pairs. So there will be a connection between your x and your y. There will be a pairing between your x and your y values, x as being your input value and y as your output. So this is an example of a relation. This is literally the set of ordered pairs. Now, this one, the one inside the curly bracket, those are the ordered pairs. You have the first component, you have the second component. First component being the x, second component being the y. This is placed inside a curly bracket which represents a set. Now this representation, this is what we call as an ordered pair. So we have different representations when it comes to relation, and one of which is the ordered pair. So we have the curly bracket, and then inside that one is or are ordered pairs. So we have also the domain here. So when you say domain, this is a set of all the x values or the set of all the first component in an ordered pair. And then we have also the range, which is a set of all the y values or the second component. So in writing your domain on the representation for the ordered pair example, we are simply collecting all those first component. So we have 1, we have 2, we have 3, and another 2, and place that one in a curly bracket just like this one. But if you try to look at that one, our 2 is not repeated or is not written twice, because in a set you don't have to repeat members of the set. And then, although it's okay for you to do not or to rearrange that one or to interchange those values inside a set, but it's better for you to arrange that one from the least to the greatest value so that there will be order. Now going over to the range, so we are now collecting our y values. We have 2, 3, 2, -2. And then again, we do not repeat elements or members of our set. So we have now the final range as the set of -2, 2, and 3. So let's go over to the second representation. So we have now the table. So literally, as the table, you have their different representation, orientation of the table. You've got the input, you've got the horizontal and vertical orientation. So this example is with a vertical orientation. So we have the input in the first column and the output in the second column, in which the input there refers to the x values. And our output there refers to the y values. So again, there is a pairing between your x and your y. So this is again a relation. So to write our domain in a table representation, we just have to collect all those under input. So we have that one as a set of 1, 2, 3. And then we go for the range. We collect the output. Then again, we do not repeat elements here. If there are elements or values of your output that are repeated, we do not repeat that one. So let's go over to this representation. Next one is through mapping. So this is now the mapping wherein we can see here lines that are connecting our input and output. We call that one as connectors. So as you can see, there is now a connection between your input and the output, and that is relation. So in writing our domain, we just have to get all those under input values or the first component. So we have set of 3, 6, 8, 9. And for the range, we have that one as a set of -2, 1, and 3. Now in the mapping, you can also write this one into the set of ordered pair by simply having that one as the set of, and then you write here an ordered pair, wherein that ordered pair will be composed of the input and the output paired together. So we have here input, which is 3, so that will be our x, and the output is 1. That will be our y. Then we separate that one by comma. Then another ordered pair. So we go for 6. And then the partner of that one is 1. Then separate it with a comma. And then we go for the next one, which is 8. And then we have negative 2, comma. And then we have 9. And then 3. And then close it. So that is how we convert our mapping into the set of an ordered pair. So let's go to another representation. So we have now the graph. So this graph is a linear graph. Now your domain and the range will be very much dependent on your graph. So all you have to do is to simply look at the behavior of your graph as where your arrow is going and what are those values of your x and your y that are affected or covered. So in here, if you try to look at that one, we've got here an arrow which indicates that it will be going on. And this one as well, it will be going on to your bottom part. So this would simply mean that if we focus on our domain, all of the values here of our x will be considered or will be covered. So that is why under the domain, we will have that one as the set of all real numbers. Now this one is an example of a set builder notation in which we have there the set of your x such that the bar here refers to the word such that x, e here is an element meaning a member, and r here is a real number. Real number meaning to say that we have our positive numbers, negative numbers, and then we have our fraction, 0, anything, and then irrational numbers. So those values are going to be considered under the domain. Now let's go over to the range. Now for the range, if you try to look at the behavior of the graph, this will also be covering our y values towards the positive side and towards the negative side. So literally that will be all real numbers. So that is why we have there a set of y such that y is an element of the real numbers. Now if you don't like this way of writing the domain and the range, you have now this one. This is acceptable. You've got there the set of all real numbers. And then we also have the last one. This is the notation for the interval. So we have interval notation for this one. Now when you say interval notation, we have here parentheses, and then we have negative infinity, and then positive infinity. This would refer to the real numbers, meaning to say your x values are going to be moving towards the negative direction, and it will be taking all those negative numbers into consideration as part of your values. And positive infinity would mean that all the positive values are also considered as part of your values on the domain. Then also for the range. We go to the next one. We have our equation. Now for the equation, again, this is also dependent on the equation, the type of equation under the domain and range. Now for this equation, we have this one as linear equation, in which the graph of this one is similar to the one under the graphing representation. So basically, you'll have there the same domain and range. So let us now go over to function. So when you say function, this is a special type of relation in which every first component is paired to exactly one second component. So take note of this one, every, and then exactly one second component. So kindly take note of that one because this is your guide in determining whether that is a function or not a function. Because when you say relation, you cannot consider all relation there as a function, only if you are considered to be a function. So we need to be careful on that one. Now, when we say function, it is mentioned here that every first component is paired to exactly one second component. Now, first component could mean this is our x values, and the second component would mean our y value. So it says here every first component is paired to exactly one second component, meaning to say that your x there must be used or must be paired, and then your x must not be used many times or more than one. So x there must be unique. There will be no repetition of your x. So that is why if we try to examine those representations, and so with the example given a while ago, just like on the ordered pair, we have the set of 1, 2, 2, 3, 3, 2, 2, 2. If we try to examine if this is a function or not, then we are to check only our first component, whether there will be repetition or no repetition on the first component of your ordered pair or the x value. So let's try to check. So we have 1, 2, 3, and 2. So this one here is now used twice. So the number 2 on the x value is used twice. That is repeated. So automatically that is not a function. So it must be that your x is unique. Now let's go over to the input. To the table. Now we are to check our input here. Our input is 1, 2, and 3. They are all unique. So that is why this is considered as a function. So let's go over to the mapping. Now on the mapping, this is somewhat confusing. So one way for you to do the mapping correctly, to determine the mapping correctly as function or not a function, is for you to count how many connectors are there on the input. So again, always consider the input. Do not be bothered about the output. So count how many connectors are there on the input. Now if you can see only one connector is attached to your input, then automatically that's a function. But if there will be 2 lines connected to one input, then that means that is not a function. Now if you try to go over to this example, we only have 1 line connecting the input, so this is function. So next representation is the graph. Now for this graph, this is, if you try to look at that one, it might be taking you so long, or it might be consuming your time to determine whether the graph is a function or not. So we have a technique for that one. We call that technique as our vertical line test. So to know whether your graph is a function or not, we will be utilizing vertical line test. So when you say vertical line test, the shortcut for that one is VLT. When you say VLT, that is the way for us to test whether a graph is a function or not. So how would we know? You can draw vertical line anywhere on your graph. So what you will be counting here is the intersection of that graph, and so with your vertical line that you've drawn or made. So this one here. Now, if the vertical line and so with the graph intersects at one point, then that means this is function. But if it's more than one, then that will be not function. So if you try to hover over, if you wanted to test out more lines on it, because you can test anywhere on the graph, you can clearly see that each of the vertical line drawn in there is only intersecting the graph once. So please do not count this is 1, this is 2, this is 3, 4, 5, and so on. That's not gonna be done like that. You only have to count one vertical line per intersection. Okay? So that means to say that you have your vertical line here. You just count how many points are intersected on that graph. And that's it. So that is how we determine whether that's function or not a function on the graph representation. So this is function because again, we have our VLT drawn there and we are only intersecting one point on the graph. So let us go for the equation. Now for the equation here, we have here our example y equal to 3x plus 2. Now for every linear equation, that is considered a function because again, if you try to look at the graph a while ago, if you try to draw a vertical line in there, there will only be one intersected point on the graph and so with the VLT. So that is why this is also a function. So always remember that when you are asked for are all functions relations, then you have to know the answer to this. Are all functions relations? All functions are relations. Because again, function is a relation. Only that it is special. Next, we have are all relations functions? Not all relations are functions because there are relations that are with a repeated value of x, which are not anymore a function. So let's try to practice determining function or not a function. So let's start with this one. So what do you think? Is this function or not a function? This is function. This is function because we do not have an x value that is repeated. Next, and by the way, the domain, we have the set of 1, 2, 3, 4. The range there is the set of 2, 5, 10, and 17. So let's go for the next one. Function or not function. You can pause this video if you want to and resume that one if you have now the answer. So the answer for this one is function because if you try to draw vertical line test over your graph, there will only be one point intersected. So you might choose drawing that one here. So as you can see, you only have one intersection on that vertical line that you've drawn and so with the graph. So that is function. Now the domain for this one, if you try to look at that one, this is extended downwards. So most likely, if you try to move down, all of the x values are going to be covered. So this is all real numbers. You can write it like that or like this one. Or using an interval notation. Now going for the range. Now on the range, you are only until here. On this point, on your y. So we are not gonna be saying that this is all real numbers, but instead, we are cutting that one until 5 there as your value for your y. And we are taking in all those values that are below that one. So we can write it as the set of y such that your y there is less than or equal to 5. Less than because the values here down are lesser than as compared to your 5. But we are considering this point here which has a value which is equal to 5. So that is why we're having here y is less than or equal to 5. Or you may write that one using an interval notation. We have there the parenthesis, negative infinity because we are taking in all those that are at the bottom part, which would lead to a negative infinity, and then until 5. So notice we are changing our symbol here. Instead of the parenthesis, we are using the bracket because this indicates that we are including 5 in our value. If that will be parenthesis, 5 is not going to be considered as part of the value of your y. So that is why we're using bracket. Next, is this function or not a function? So try to pause the video and resume once you are now with the answer. So this one is function because as you can see, if you try to count the number of connectors here on your input, you've got only one connector on your input, so that will make it function. So the domain the domain here is the set of 100, 200, 300. And the range is the set of 1, 2, and 3. So next, function or not function? That is function. Because your x values are not repeated, so that is why it's a function. Going over to the domain, so we have the set of 2, 4, 6, and the range is the set of 3, 5, 6. So is this function or not a function? So again, you can pause the video and then resume that one once you have the answer. So some of you might be thinking that this is a function, but this is not a function for the reason that there is one input that is not paired to any output. Remember, on the definition of the function, every first component must be paired to exactly one second component. So we have here 5, which is part of the first component or the input, which has not been paired to any output. So this is not a function. And the domain, we have -2, 0, 5. Range is negative or set of -4, 9. So let's go over to this example. So this one is not a function because again, you've got here 4 and another 4 on the x value, a 5 and another 5 on the x value. So that's not a function. Domain, you've got the set of 4, 5, and the range is the set of 5, 6. So what about this one? Is this function or not a function? So some of you might be thinking that this is not a function because of this one here, but indeed this is function. Now, why is this function? This is function because, again, as I mentioned a while ago, do not look at the output. Just concentrate on the input. Now, counting off the number of connectors here on your input, we've got 1 for each, sorry. 1, another 1 for this input, and another 1 for this input. So this is a function. This is unique. So the domain here is -3, 3, and 4. Or again, as I mentioned, you can just interchange the members there or the values there in a set. But the proper way of writing that one should be set of -3, 3, and 4. We're arranging that one in order from least to greatest. So let's go over to the range. The range is the set of 9. Let's go for this one. So what do you think? Is this function or not a function? So once again, pause the video and resume once you have the answer. This is not a function because again, if you try to draw your vertical line here, you can see that this is intersected here and also this one. There are 2 points being intersected by that single vertical line, and that's not a function. The domain here, based on the graph, the domain, we do not have the real numbers here because we are only until -1 as part of the x values and then moving towards negative infinity. So writing the domain there is the set of x such that x is less than or equal to -1. So if you try to look at that one, that's less than or equal to -1 because you got there on the left side, they are smaller as compared to the right side values or numbers. So if you try to look at this, you can also make use of the symbol here. This is telling you that the values are on the left side of -1 because the tail is pointing to the left. Or you may use the interval notation here. Now this should be a bracket. So this should be a bracket because if you try to look at this, we still have -1 in this particular point of your graph. So meaning this is included. So you will have this one as a bracket. So we have -infinity, -1, and then we have a bracket for that to indicate that -1 is included or part of the domain. Then we go for the range. The range there doesn't have a problem at all. If you try to move that one as your graph there opens wider, then all the y values are going to be considered. So that is why we're having here all real numbers or this one. So next, let's go for this one. Is this function or not a function? Some of you might be considering that this is not a function because of this one here, but this is function. Because again, as I mentioned, do not put your attention on the output, focus on the input. Just check how many connectors are connecting your input. If there's only one for each, then that's a function. So domain here is the set of 2, 4, 6. Range is the set of -2, 0, 3, and 6. So I think that's it. So thank you for watching.